It's going to be session 1B, managing increasing complexity in the control room. And we have John Simonelli, who used to work at ISO New England in the control room. And John Simonelli is now with Flashover LLC, and he'll be chairing the session. Thanks.
Good morning, everybody. Just curious, how many people here actually work in operations or work with groups that support their control room? Oh, good. We've got a few folks. Yes, as people in operations know, it's organized chaos and things are going to get worse. The days of being in the control room now are complicated by the way things have changed. You've got to track weird things like wind forecast and irradiance so you can track what your resources are doing. You've now got to track charge and discharge state on batteries on the system. And then there's all those wonderful things called GETs. So you've got ever-changing dynamic line ratings in the control room. You potentially have some of these topology processors that want to recommend opening circuits, opening breakers, changing dispatch, committing units, and then throw in things like dynamic flow control. So what used to be chaos is now exponential chaos. And so that's kind of what the genesis of this panel is. Opportunity for some folks to talk about the problems and challenges they're seeing in their system and some of the things they're looking at doing to fix it. So we have an interesting panel, and the first speaker is going to be Rajiv, who is from the Indian power system, and he is going to be presenting remotely, unfortunately. So I guess Lacey's got things all set up for him. And we're going to do Q&A at the end. So the speakers will all go through their presentations. And then hopefully, if everything's on schedule, we'll have about 15 minutes at the end for you all to ask a lot of good questions.
Morning. Are you able to see the screen?
Yes, we can.
Okay. Thank you. So thank you for the introduction. And I understand that this is regarding the managing increasing complexities in the control room. I will not be I understand that as the introduction was given that we are definitely a lot of complexity in the control room as the wind, solar, and all those issues and new issues about the inverters is already being there. They've been talked about. Today, I will basically mainly discuss about the HVDC and STATCOM, which are there in an Indian power system and how they are behaving in the change environment, because a lot of changes in the power flow directions, and therefore we need to take a lot of help from these new resources which has come. They are not new resources, they are older one, but now we have to more and more rely on these resources for different things, and therefore some challenges has been observed in the control room. So that what I will be discussing today. So the content of my presentation is overview of Indian power system, then HVDC network in India, operational experience of HVDC in Indian power system, future consideration for the HVDC design, and similarly operational experience of STATCOM in Indian power system and future consideration for STATCOM design. So this is what has been basically faced in the control room. So that is what we are presenting. So dimension of Indian power system, as you all know, we have around 500 gigawatt of installed capacity. We have met a peak load of 250 gigawatt and daily energy demand met of around 5 terawatt hours, around 5.5 million circuit kilometers of EHV transmission, 242 gigawatts of renewables we have, including large hydro of around 48 gigawatt. We have 5 regions in the country, so around 120 gigawatt of interregional capacity. We have 14 HVDCs and then 3.2 million circuit square kilometers of footprint, 1.4 billion people you all know, 4.5 gigawatt of we have international exchange with our neighboring countries such as Bangladesh, Bhutan and Nepal, and very small quantum with Myanmar. And then around 171 terawatt hours of annual market rates. We have 3 power exchanges, and this 171 terawatt hour is out of these 3 power exchanges. Mostly our transactions are PPA based, say long-term tied up, not going through power exchanges. around 6,000 plus market participants are there, and around 1.18 million market transactions take place daily. So this is what the energy distribution map of India looks like. In north and northeastern, we have very good hydro, and also in southern region. Then we have a very good thermal, basically coal-based thermal power plants in the eastern and western India. Then we have around, say, RE, solar and wind energy in the north, west, mainly western part of the country, and southern part of the country. And so this is what our map look likes about the resources. We have the existing transmission infrastructure is around, again, 0.5 million circuit kilometers. I think in the first slide it was 496 K circuit kilometers. Here it is because the date is different. This is data is for April 2025. There it was for the August 2025. So we have a great power system where there are a lot of flexibility is available in the transmission system, and we utilize that flexibility. So this is what our HVDCs look like. In this case, we have slightly one more HVDC which will be coming in future. That is we will be getting connected with the Sri Lanka. So that is in the presently in planning phase. That will also come up, but otherwise we have around 14. That too also is one international, that is HVDC Bheramara back-to-back interconnection is basically with Bangladesh. So if we exclude that, then it will be 13 HVDC interconnections we have, which comprises of long distance HVDC as well as back-to-back substations in the different part of. Earlier, basically, when we were operating 5 regional grids individually, these HVDCs were working a interconnect between these 2 regions, but now presently we have entire country is synchronized in as a one AC system. So therefore these HVDC work in parallel to these AC systems along with that. So that has been quite good. That has given quite good flexibility. We can change the power order and change the lot of congestion management as well as voltage regulations. All these things we can do very effectively. So this is what, again, these again numbers which were there in the last slide, again same numbers. So mostly they are LCC based, and one is HVDC is on VSC based HVDC. So we have flexibility in transmission, controllability of active power in both directions, connection of asynchronous gates. Earlier it was there, no longer now, except that we are connected to Bangladesh with asynchronous as a asynchronous link of back-to-back connection at Bheramara. And a long distance bulk power transfer with lower losses, voltage support from the VSC based HVDC. We have been starting black start capability of VSC based HVDC. Also, we are exploiting reduced transmission losses. Definitely, this will be with the same compared to similar AC system with same power capability. And interconnections benefit has been the cross-border exchange facilitating electricity trading different directions. So as in one important point in the last slide was that we have say back-to-back and long distance these bipoles. Some of these bipoles which are 6,000 megawatt, these are the basically multi-pole HVDCs, and one HVDC is Vishwanath Chariali Alipurdwar. This is a multi-terminal HVDC, multi-pole and multi-terminal HVDC we have. So again, coming to this behavioral change in power flow because of lot of renewables has come. This was discussed earlier, that because of advent of renewables, there is a lot of change in the power flow directions. So earlier, mainly the northern region of the country used to draw a huge lot of power from outside the regions, which were surplus in the thermal power portfolio. But now with the advent of renewables, this has slightly changed and direction of flow has changed drastically over. Not only this is the only between northern and western region, but in other regions as well. So this is what have been the flow directions of different HVDC, which we keep on, say, changing in daily or say annually or seasonally. We also, there is a lot of change, and then also on a daily basis, there are a lot of changes in the power order. So this is all along everywhere this takes place. It is nothing new, but we are just showing that we are utilizing and in different direction. It is required, and only on the same day, it may be required in the both the directions, positive and negative, because of solar being available during certain times or wind being available during certain seasons only. So this is what, again, reactive power support from VSC based HVDC we have been utilizing. Very good that this is not related to the power flow, which is constraint in the LCC. So VSC is definitely helping out in that session, that each terminal can work as a separate STATCOM or reactive power source or sink as we wish to do that. This black start capability also of this say symmetrical pole HVDC has been utilized in both the directions. And this has a basically as you see that interregional SBC power order changes during COVID period was significantly lower, while nowadays they have significantly changed because a lot of change is required. If this was comparison only for April 20 to April 21, but if we see nowadays, this will be much higher changes would be taking place. So what challenges being faced in basically HVDC? It is not related with HVDC basically. Only relation of this event with HVDC is that this a multipolar HVDC trip. Because of that, there was a voltage drop because of filters going out. So there was some voltage drop at this location. But further to that, there were significantly higher voltage drop took place. And this resulted in a lot of, say, single phase motors getting installed. And then also the AC, this was a day in June in India's, which is a highly, say, summer season. And this summer season, a lot of air conditioners were on and this particular northern region. And therefore, a lot of ACs and single phase motors were available in the system. So they stalled, and then again the voltage drop took place, which a lot of ACs gone out of say system, and therefore there were significantly loss of load in the system, which was much higher, say, loss of load to the system, and then frequency jumped from 50.03 hertz to 50.68 hertz. This also caused very high voltage because of less power flow on the high voltage transmission system. This resulted in a very high voltage in the different part of the network, and this caused the tripping of large number of transmission element. 23 numbers of transmission line tripped on high voltage, 1.1% per unit. Basically, this was the 110% was the setting of the high voltage setting is there on 765 kV and 400 kV network. So around 16 gigawatt of load disappeared from the system immediately, and then again it came back also. It is not that this remained out of there, it came back slowly. And so this was despite 2 DMR. The main point is that despite 2 DMR, we could lose. Basically, there was a fault in one of the DMR. Despite having very high degree of reliability of 2 DMR, if one DMR goes out, other DMR is only getting connected through a isolator, and it was not through a so therefore both the DMR went out, and therefore all the 4 poles of this multi-pole HVDC tripped. So that is the main learning from this event, that we must have good philosophy about the DMR also. Even not having more is not always good. So technical requirement of HVDC operational experience, which we have seen that most of the upcoming HVDCs are planned in the large RE complexes. Now, since we are coming up with very large RE complexes of say 150 or 180 gigawatt in very small concentrated area, or 40 gigawatt in very small area of say only 50 square kilometer area. So therefore we need high degree of, otherwise we will require a lot of AC systems, 765 kV lines also crisscrossing. So we need high capacity of corridor. That is why we are planning for the HVDC system. But HVDC system, these HVDC system, again there is a lot of debate about the LCC versus VSC based HVDC. So if we go for LCC, definitely there will be, at times there would be quite low system strength. So how they will behave during those things, that will become important. So those are the reliability consideration has to be there for the future design. They should be able to operate successfully in low system strength, ability to ride through fault, and impact on voltage oscillations. In the renewable rich area, we are also finding some voltage oscillations because of, say, again, this issue is related with the PPC control loops, how much delay is there in different PPC control. Therefore, there are happening some voltage oscillations, which can again impact the HVDC operation. And we have seen that these HVDC sometimes misbehave when there is a very low fault level. We have seen that again oscillations also observed in some of the areas. So therefore we are saying that let us plan and new HVDCs which would be able to sustain that. Then fast power reversal, that is again a time. Earlier there were not many, say, changes in the power order, but now we have to go in both the directions quite frequently because of interconnection in the system. So therefore there will be requirement about the fast reversal of power order. So for back-to-back stations, this has been quite fast. In significant time, within minutes, we can change from one direction to another direction. But for the long distance HVDC, this has been a problem. It takes a lot of time because again, not only from the technical perspective, but from operational perspective also, a lot of time is taken. So therefore, there will be requirement for the both the directions, how fast we can change over from one direction to another direction. Overload capability under prevailing weather, especially extreme temperature conditions, also requires that we should have at least overload capability, which is able to sustain during high extreme temperature conditions as well. So high reliability of these HVDC system is required. So coming to operational experience of STATCOM, we have already said around 19 or 20 STATCOMs are there in the system. Most of our STATCOMs some of the STATCOM are based on the voltage, based on these, they are sided with the MSR as well as MSC in the system. So these MSR and MSC are there so that we can have slightly wider range in our say dynamic support. And some of these STATCOMs are based on the voltage switching criteria. Some of they are current based switching criteria. So what we have found out that wherever these current based switching criteria is there, they have certain issues operationally. We have seen that there are certain issues. We are going with the more than 15 STATCOM further under planning and execution stage, mostly in the bulk RE complexes. So this will also further increase our number of STATCOM in the system. So this is again a chart that this STATCOM helps the system to during any fault. They definitely are providing a lot of reactive power during fault condition and then reverse case also. So they are quite helpful. But in case of say these technical issues with STATCOM and is that MSC and MSR switching logic, wherever this is not based on the voltage, this is based on current. So there is no further setting. This only we have to set the V reference value in the STATCOM. And then it will take care of all the switching of MSC and MSR. So what happens that during some of the cases, this if MSR is there, so generally our dynamic support comes before the any switching of MSR and MSC. This MSR and MSC switched only after certain percentage of say current is there in the VSC. So therefore, our in all these cases, the dynamic portion comes before the static portion. So that is one issue. So some of the event, if some event take place, there is a static portion already in the system. This will not give us the full dynamic range of even the dynamic portion, because if MSR is there, the next portion, next is say like that event is there, wherein one of the say MSR was in service before the operation, before the any fault taking place. So in the next side, it went only up to plus 123 MVR only during the fault condition. Might have given much better response if this MSR had been out. So because this cannot switch on, switch off very fast. So therefore, this consideration is there. So this is one issue. We are not able to utilize full dynamic range. Second is that whenever there are oscillations of, say, certain degree oscillations are there of one particular hertz oscillation are there, say 4 hertz oscillations in the system, then these STATCOMs reduce their gain, automatically reduce their gain. So what is happening? They are basically enhancing the oscillations because of this lower gain. This is again a say safety feature as far as this design of these STATCOM is concerned, that they should not participate in the oscillations, but they are turning out to be in the reverse direction in the high RE rich areas. So that is another gain reduction is another issue. And then we are converting them to the fixed Q mode operation to the STATCOM. Therefore, again, we are losing their dynamic support in the system. So that is basically one of the issue what we have. And then the third issue is that voltage right through of IVR versus STATCOM. So when we want that IVR should remain connected up to 0.15 PU voltage, and again there is a curve, most of the countries would be having this type of curve, but the STATCOM are slightly within that, at least for LVRT, that they will trip as 0.3 per unit voltage. So therefore they will go out of when even, so this will again jeopardize what for this LVRT settings has been there for the, say, our renewable plant. So therefore again this is also another area wherein there is a need for improvement. And another area of is that there is a slight delay in MSC and MSR. So if that delay could be avoided, therefore again this could also help in the future operations. So STATCOM controller design shall ensure stable performance during oscillations. LVRT and HVRT settings of STATCOM shall be more robust than VRE plants. And the switching logic of MSC and MSR shall be based on bus voltage, as we are already having some of the STATCOM which are based on bus voltage. So there is a lot of flexibility. We can switch on, switch off the MSC and MSR as we like. We can change the setting, but in case of current-based logic, we can't change any of the settings. Switch in and switch out settings shall be configurable. Time delay for switching in and out of MSC and MSR shall be configurable in a large range. Rest time for MSC and MSR may be optimized, reduced to handle successive fault in short duration. So this is what my say discussion points are there. They may help the population available in this conference room, that they might also might have faced similar issues or may face similar issues. So this is again from my side. I will be very happy to say answer any questions, further questions which may come out. Thank you very much.
Thank you for joining us from India. We appreciate you taking the time out of your day. And our next presenter will be Alexandre from RTE France.
Hey, good morning, everyone. So I am Alexandre Parisot, and I'm going to be bringing the perspective of the R&D division of RTE to this topic of increasing complexity in the control room. So RTE is the transmission system operator in France. So essentially, operates, maintain, develop any transmission infrastructure in a metropolitan France above 50 kV, which is in France, which is the limit between a DSO and a TSO operation. And the RT is a TSO, which means it's both a transmission owner and a system operator, so that you can navigate a little bit with the different responsibilities. And so here, what I want to do is illustrate some new innovative way of solutions architecture to deal with increased complexity in the control room in a very specific situation. But this is going to give you some idea about what's the way we think about it and how it is actually deployed in practice. So the starting point here is integrating renewables and high level of renewable in a sub-transmission. So in France, that will be 63 and 90 kV. And so what we've seen is, if you look at some lines, what you see on the left is with very high wind penetration, what used to be something very simple in terms of flows, consistent flows along the year, is starting to move up and down with a lot of variation. And so how do you deal with congestions, with thermal overloads of lines and the situation? Of course, what you need is to strengthen the network where appropriate when you're trying to increase the share of renewable and integrate more wind. But usually when you do the planning and when you do the interconnection, you also provision for the ability to curtail some of that wind in situation where you have stresses in the system. So most of our interconnection agreements will include the provision that in order of like 10, 50 hours a year, you're going to have curtailment. Then it comes down to operations to actually manage that. But you can see that with this kind of complexity, there's already the idea that that might require a lot of manual actions, that might require a lot of things. But also, you're not exploiting all the flexibility that you can have, because many of this, there are a lot of actions that you could take that can happen actually really, really fast. And so the concept was to develop a new automatic controller, which we call the NAZA, and essentially looks in real time at the system, look at the transient current, the capability, DLRs, network topology, and minor situation, and determines, depending on what's happening in the system, either in normal conditions or post contingencies, what are the optimal actions that you can take in order to mitigate any kind of contingency that might happen. And so what you can do is you can reconfigure the network, so do topological actions, which can happen very fast. You can do limitations on the wind or your PV generation. You can change just the set points of batteries. You can do all these kind of things. And the way this works is it operates on a 15-second basis. So every 15 seconds, it looks at what has happened, if any action needed, and what is the sequence of action that would ultimately deal with this. And it takes the first action, and then comes back 15 seconds later and see what's happening. And within 15 seconds, most of the actions that are described, they can actually be they can take place. Usually, you can have the actual response there. In terms of implementation, the logic between this is what we call a model predictive control. So you're essentially taking all of the input data that you need, compute threshold, determine interconnected component, do a state estimation, And then the model predictive control determines that the optimal sequence of action, taking into account what's available as levers, what are the costs, and then execute the first step of this. So this is a closed loop system essentially, because it's every 15 seconds it comes back to it, and the idea is that after a series of steps, you're going to come to a situation where the congestion is no longer an issue. So to give you an idea of what we're dealing with a little bit closer, this would be like an illustration of actual operation, and this is also to give you a sense of the kind of network configuration that we're talking about. So these are mesh networks, but these are sub-transmission networks, so they are not essentially very large. But there's still a lot of things that you can take on a single contingency, depending on the flow, on the local conditions, on what's going on. There's still a lot of complexity in the levers that would be optimal in this situation. And here you can see if you have a constraint on the line that's marked in red, within just 1 second, the system just determined that it would send a limitation on one of the lines, and then determine some additional actions would be needed, and then comes back later and determines that this was actually resolved. And again, you can see that it's not, you're not dealing with the entire network, but you're not dealing with something extremely local. You're already reasoning on something like about 10 to 20 substations. In terms of implementation, so this has been implemented in RT's own data center, so that run also our EMS system, and basically within the time that I described, these 15 seconds, you really have the time to essentially collect all of the data, run the optimization that takes just a few seconds, just to send the order. You could philosophically, or you could in terms of architecture, think that because those are local decision, you could actually implement the algorithm in one of the substations on this network, and essentially come up with a decentralized way of doing things. So we figure out for this particular application, getting everything back to a centralized data center in France was completely acceptable, and but again, also a more decentralized logics would actually be completely possible. And you've got all the interactions with all the system, because you have also to interact, of course, with the actual customers. You have to so a generator, batteries. You have to interact also with the SCADA of the DSO, because the orders, if the levers are actually addressing generation that's on the DSO side, this has to go through the DSO, so that they can make sure that the lever is actually compatible with how they run the system themselves. And in the control room, the NAZA logic happens generally faster than any way the operator can actually react. So it's just knowing that this thing operates, but it has of course the way to look at the configuration. Is everything right? Is everything in order? Is the system working well? And if there is an activation of the system, there is also an interface where they can see exactly what was activated, why, what were the sequence of actions that were taken after the fact. And so this allows the operators to still have a little bit of control, but again, that happens faster than what they can usually handle. In France, and we usually consider that for a simple remedial action, 5 minutes is the usual time, and for a complex action, 20 minutes is what you need. So here you see that we are dealing with reconfigurations or actions that are on a much faster time scale, but which allows you to exploit a lot of the overload capabilities of the lines. In terms of actual deployment, so I showed you an example of actual application right now. So as of February this year, and the number is actually higher now, but this logic has actually been deployed in actual operation on 19 zones in France. So this gives you a little bit of the size also of the zones, so we're talking about things like 300 lines that are monitored by all of the combined systems, 500 substations, about nine gigawatt in the system, and the system doesn't necessarily need to control everything to be effective. So all of the generation is not available as a lever. Reconfiguration also usually is not needed to have like every breaker or every possible configuration. Usually like a couple of breakers are enough just to deal with the usual way to reconfigure the system. And the goal is to keep expanding this to reach like probably 100 of those throughout the system as needed and as enabler of increased renewable integration in the system. So now perhaps one of the questions that you may have is, okay, well, I mean, how is it really different than usual SPS or a remedial action scheme? And so I mean, in this thing, you can see that because we're dealing with a mesh network, it's already a little bit more complicated than most of the usually sequential radial things. Here what we're really doing is as an optimization, running something that goes far beyond just a sequential flowchart where that traditional RAS or SPS usually use. You can either consider it like an extension of those, or you can consider it like something completely different, like a mini EMS, an autonomous EMS that would run on a very small area on a larger time scale. And of course, with the question with the coordination of the protection system as with the correction of the actual control room operation. And the where it also differs is, you get a lot of flexibility in this. Technically, you can extend this to any form of GET, any form of control. So you're going really one step beyond what you usually do when you plan out a RAS or SPS system. And where that brings me is, if you really go a little bit even one step higher, you can say, well, this is a little bit of an evolution from our usual way to think about the architecture of the system. Usually, you had the idea that you had a protection layer whose only function was really to make sure that you don't have overloads in the line. You're dealing with safety. You're dealing with all this kind of thing. Those are very simple. Automatic systems that react really fast, that are supposed to be extremely reliable, but they're not supposed to be really that smart. Basically, you're really pushing the needle to reliability and making sure that they operate in a way that you can completely predict and that you can do it. And at the other end of the spectrum, you get the control room operations, which run manual actions, a lot of automatic closed loop system, but usually that operates in a matter of minutes. You get the markets, of course, and here you're trying really to optimize things to get to an optimal running of the system. And you see that here, this NAZA automaton doesn't really fit very well in any of those two categories. It starts to be in somewhat of an in-between layer that's more of what we can call a control layer that operates in a matter of seconds. So it's faster than what your operator can actually can usually deal with, but it's actually slower than your usual protection system, and it operates actually in conjunction of those. The way you can think about it is the protection system would be your airbag system, and your car is not very smart, but it's supposed to do its job of actually protecting the system where really things go wrong. The control room is more like your GPS navigator, so it's not gonna avoid you to have any kind of crashes or whatever, but it's gonna get you there. And then you've got something in between, which is more like your safety system in between, which is gonna help you drive essentially. Basically, this conceptual idea is really one way we have been thinking about this, and which is illustrated by this NAZA system. And so with this, I'll be happy to answer your question later on in the panel. Thank you.
Thank you. Okay, next on the panel, we have Tasia from ERCOT's going to speak, and she's going to tag team with Chung.
Hi, good morning, everyone. This is Teja with ERCOT. It didn't go to the screen. Let me do it again. I'm sorry. Right. Oh, no. We'll make sure everybody's got enough coffee. That's right. All right, well, Lacey's setting it up. I think I'll just go ahead and introduce myself. Thank you, Lacey. Like I said, I'm Teja with ERCOT. I am joined by Xiangjun, my colleague at ERCOT as well. And I am here to talk about Gridgeo, a situational awareness tool. Let's see, all right, I'll just go with this. Well, we have heard so far about how we're all dealing with the complexities on the ever-changing, evolving grid in various forms. And one of the things that I am going to talk about here is the tools that we make available to all the operations teams, right? Primarily the control room, but also many different teams that support the control room. Just going, sorry. 1 minute. Oh, there we go. All right. So just a brief, if you look back in the last 5 years, and I'm sure all of you will relate to this, is if you look back in 5 years, what was your system looking like 5 years ago, and what does it look like today? In the 3 markers I have here is look at the number of buses you had in your system, look at the number of generating units or all the equipment that you have in the system, and then what is your peak demand. Specifically with ERCOT, you can see that we doubled or more than doubled on many of these things, right? The buses went from, and I'm just comparing with 2020, not even going behind that, right? So our number of buses is close to 10,000. We have doubled on the number of generating units. And I won't even get into the different types of generating units that we're dealing with, the different fuel sources and all of that. And the demand, we're almost close to the 85 gig. With all of that, it becomes very, very complex to manage all the different components it takes to meet that one single managing the reliability of the grid, right? Which can translate to many different things, right? We're talking about the frequency control aspect of things, power balance, right? We're talking about the congestion management, all of the security of the system in terms of thermal violations, voltage violations, all of these things boil down to how do you provide tools for your control system to be able to, for your control room to be able to look at a single application instead of toggling many different screens and saying, this is a problem that I need to deal with right now, right? And that's what this is the tool that I'm going to present. And then Xiangjun's going to dig into some of these screenshots. But all of this complexity points to the need for a single situational awareness tool that is built on latest technologies that not only provides accurate real-time information, but is also very, very user-friendly and can be used by different users with different backgrounds, right? The control room, grid operations, market operations, the planning teams, as well as some of our external participants as well, external market participants. And just a brief history of what we used to have in the control rooms before 2011. If you look at that, the EMS, the energy management system, in combination with the PI historian, was the one that was available. You toggle different screens, look at many different things to get to all of this information. Then between 2011 to 2018, we had a tool, Macomber Map, which was our first attempt at how does the system look on the map, right? If I'm looking at congestion, where in my system is this congestion, right? But then we took that another step. And in 2018, we have Gridgeo, which is the tool that we're presenting. It is a geospatial browser-based HTML5 canvas for the entire ERCOT system. And it's, formally speaking, very cool, right? It gives you the entire Texas map. It gives the ability for the users to drill as narrowly as you want, or to dial back as much as you want to look at the entire system in conjunction with different filters and many different functionalities that are very, very self-explanatory. And that was the intent of building this tool. And it has evolved quite a bit from 2018 till date. We have almost 450 internal users, and we have about 100 external users. So one of the considerations you can think about is also the performance of it. Like I said, it's a very, very fast real-time tool that can pull data from many different sources and make it available on a single screen. And that's what the framework is, right? I'll briefly go into the different inputs and the technology behind it. The inputs are, we use the network model. The data from the energy management system, there are bits and pieces that we pull from the historian that give you an idea of how it looked like a few minutes ago versus what it is right now. And then the very interesting thing is also the weather layouts on it. As you all know, the weather is a big part of our operations. And that's one of the things that this tool provides in conjunction with all the other data. As you can see, there is the entire Texas grid map, and there is the regular station one lines, but also the very key feature and something that's very helpful to the control room is the multi-station one lines, where you can navigate from one station to the other and link to all of the different connectivity points there. We have it available in different forms. I'm going to skip over that, but these are the different data inputs, the weather data, like I mentioned. And the energy management system data sets are the real-time data sets that I'm referring to. We have 2 to 4 second data sets, 10 seconds data sets that do keep this information very, very real-time. So decisions can be made based on data that's available on the screen. Just digging into the business use cases, right? Like I mentioned, situational awareness is the big thing. As Xiangjun goes into some of the other slides that we have, you will see the various filters that are available, the contour maps that point to the voltage in the system, and also the multi-station one lines. We do also provide the ability for look-ahead studies, right? In your energy management system, you have ability to run studies. The Gridgeo application does have the ability to pull the data from your study and show it so that you're able to look at how does my system look like maybe 1 week from now, right? If I have the network model for 1 week. We go all the way in the back. We're able to pull data sets if you have a older model all the way back, maybe even 6 months. And to the future, we run studies up to 60, 90 days in the future. So Gridgeo has the ability to present all of that data to the engineers as well. So not just the control room. So we have Study Pro, Study View. These are tools that, these are the functionalities within Gridgeo that will help you to run the studies and show it to the users. And then, like I said, the hurricane, storm, cyclone trajectories, and this is not just limited to Texas, it shows the entire globe. But mostly the relevance to Texas is, you know, you can see the weather systems that are coming into your system. So you know whether you need to be planned for it, where is it hitting, our control regions, things like that. And then one of the very key functionalities is also that we use Gridgeo very actively in our operator simulations. So the control room is, you know, trained on using Gridgeo in various extreme weather scenarios, emergency scenarios, black start scenarios. So this tool does have the ability to simulate all of those scenarios as well. And then the external part is providing situational awareness to our TDSPs and NERC with different levels of access control. So we do make it externally available as well with different roles and permissions. With that, I think I'll hand it over to Xiangjun so he can walk through each of the slides.
Yeah, good morning, everyone. My name is Xiangjun Xu. I'm the manager for the markets and UI development group. Gridgeo is one of our main UI application. And as Teja already mentioned, initially this Gridgeo was invented as a situation awareness tool, but over the time adding more functions. For example, now we're supporting study, right? So outage schedule, outage coordinators can use the tool to look at the future models and apply outages and see if they're causing any violations. Because the capability of Gridgeo, they can easily see from a system view on all the lines, all the violations, and also we recently add a two-way communication. We can send the control commands to the DTS to simulate generators, control generators and the load, also open close breakers. So this become the essential control for the simulating black start. I have some screenshots for that. And also because this tool, we open it up to the market participants for the TDSPs to look into this so they can access Gridgeo. So we have an instance for external users to access it. So yeah, this is the main interface. Once you log in, you will see the entire map of this Texas grid. If you turn it on, you can see all the map layers, but right now normally we don't turn it on for performance reasons. This one has multiple layers. So this is the layer, actually all the lines, every kV level has their own layer, so you can turn it on, turn it off. All the substations also has the same. There's multiple. Example, this one is a substation filter. So you can turn on with them if you want to check which substation has which kind of generator units. We have all those kind of filters based on the fuel type, or we add the ESR, DTR. So you can also, if you check those, we only show those substations has those generating units. So you can easily see where are those generating units located. Besides generator filters, we also have load filters. So if you want to see maybe where are those some large load located, you can use this load filter to easily see where they are on this TGM. Here is the transmission filter. You can filter by kV levels, and also we can easily see all the line flows. If you want to see the flow above certain percentage level, you can turn it on and then specify your loading level, and then we will show those lines above those loading levels. Here is the one line. If you click on the TGM, click on any substation, we will pop out this one line diagram, giving you more information about what's inside the substation. This one line is exactly the same as what we have in our EMS system. So during each model load, we will creating one lines for every substation. So in this substation, we have a ESR. So we also show the ESR charging status and also all the equipment list in the substation. So if you click on here, we'll pop up all the data for that particular equipment here. Here is the multi-station one line. So if you on TGM, you select multiple substations, we will link them together and show both substations. Here's we have this tool to show all the real-time violations. Those are the results we can show either from contingency analysis, RTC, or we can based on the SCADA. We can see both the voltage violations and the line flow violations. Those substation has high voltage or low voltage will be highlighted. And then you can, if you want to see where there's a function to turn on the flashing, you can easily identify those violations. Also, the tool can show all the voltage scheduled outages. So this is a very useful function. As I mentioned, the outage coordinators use the tool, right? So you can click on the outage, see where they are located. This one, we have the control function, right? Because initially this one was designed as a situational awareness tool, so you can easily see where are the low voltages. Blue ones are the low voltage, high volt. I think blue one, it's the low voltage, and then there's some high voltage. It's this one. You can see it's a high voltage. And we have multiple weather layers. You can overlay onto the grid map. Yeah, this is the radar layers. Wind layers. Wind layers will be very useful for you to see the predicted wind generation. And we have the solar, so you can see easily. And then you can zoom in to see. And this one combined with that filtering, right? You can see if there's a solar generating units, then you overlay this solar forecast. You can predict see what's the future generation of the solar generating units. And then, of course, we have some actual layers. This is giving you the Metator, the temperature forecast. This one, the hurricane. You can see there's a hurricane coming, and then what's the impact path. There's some additional weather layers, icing, fire, and tornado for example, right? And then this one is part of that violation interface. You can see the interface, right? What's the violation? The interface involves multiple lines, so yeah. And if you want to look into a particular area, you can LISO. So this one will give you the summary of all that area you selected. Yeah, and then in this LISO or entire system, because we divide by all the equipment types, so DGR, DSR is a tab. You can select, see what's in that area. Yeah, all the DGR is DER resource in that area. Yeah, and also from system level, we have the total ESR charge. You can see the total levels in entire ERCOT. Yeah, and we add, as I mentioned, we add the simulation support. So we have this generator control panel. You can start up a generator and synchronize it. We have a sync scope. You can sync it into the system. And we have load the control panel, and also this one is the breaker control panel, has the sync scope also. Yeah, that's it. Thank you.
Thank you. That I gotta admit, that's pretty cool. Next presenter is Vikas from EPRI.
My slides here. All right. Yeah, so I don't have a lot of cool graphics to show, but gonna show some of the things which we are working at EPRI and what is our vision from, how we can address anything we see from a control center of the future perspective. How can we be ready? So again, I can take 10 minutes to talk about EPRI, but you can read through it. So we can basically bucket all the challenges we are seeing into three broad categories. One, looking into how can we be ready to operate high inverter-based resource systems, what tools we need, what processes we need, how can we train our personnel operators to be more ready for such high inverter-based scenarios. Second bucket is looking into how can we improve utilization of existing transmission grid to better support integration of renewable resources. So that's basically how can you operate your grid enhancing technologies, how can you optimize reactive power, active power in your system. So that's one bucket. And third one is resilient operations is basically looking at all the recent events, blackout, which has happened, how can be more resilient to such events. So that basically the broad category under which I think we can categorize all the challenges we are seeing from a real-time operational perspective. From opportunities perspective, there is AI, which, especially the generative AI become more and more disruptive. So how can we use that in control center, not replacing an operator, but how can we use that to help operator to make better decisions? So that's one area of opportunity. Data, there's a lot of good quality of data coming through PMUs, new sensors, other devices. So how can we leverage that data to inform operators? And last but not least, we have increased in computational capability. So how can we now do more optimization from a real-time perspective? How can we use some of these computational announcement to improve real-time operations? So that's basically summarizing some of the challenges and opportunities we have. So what we are doing at EPRI, basically starting with even building a roadmap for different utility members, like what do you need from future perspective, what data and models you need, what technology, what tools you need, what kind of process can be more automated than being manual, like can you use some of these latest technologies from voice, data, text, how can you use that to make some of these processes more automated? Also looking into how can you better display some of the information which comes to the control center for operators. So human factors is a big thing with respect to developing these roadmaps for the control center of the future. And last but not least, how can you improve the facility design, more ergonomic, how you make sure that you have right amount of displays, and how can you make sure like operators are seeing what they want to see on those displays. So that's basically one of the area we're working on. And this basically, probably this is the only colorful chart I have in my whole slide deck. So this shows a quick schematic of our vision of control center of the future. Again, the green is sense making. The yellow is sense making. The green is decision making, and red is action making. You can see the operator is still in the center of decision making and getting a lot of information from the tools, from the data, from sensors, and making sense of what's happening in the system for more better situational awareness. Then also you leveraging some of the tools from a decision making perspective, and then taking actions, and in all that it's getting fed through real-time data from assets and infrastructure. So this is basically our control center of the future vision, where operators sitting in the middle and looking at a lot of data, making sense of it, using the tools to making some decisions, and then taking actions on it as well. So that's one area we've been actively working on. Also now looking into some of the things we are working on, how AI can be used. And again, I'm not saying AI will be replacing operators or AI Sentinel will be doing everything autonomously, but making sure that how we can smoothen those rough edges from an operator perspective. So help him make some improve its decision support capabilities in real-time operation. So one of the things we are working on, and one of the main things you operators always get inundated with is a lot of alarms, and how can you manage alarms, how you can make sense of those alarms, how can you do root cause analysis based on those alarms. So something we are working on, can AI be used safely from a transmission alarm and operational data perspective? So we have a novel prototype concept here, which we call Alarma tool, which basically takes all the alarm data, network data, put it together. But there's a lot of challenges when we started working on this particular concept. So looking into, when you're talking about alarm data is very semi-structured in a lot of this SQL kind of databases. Even from an AI LLM perspective, they do not understand, recognize words and text and acronyms, when you're talking about alarms. Also looking from a network perspective, alarm data is very much disconnected with the network data. So those are some of the, just from a network perspective, but also from AI perspective, you see, AI can give you, they can hallucinate, and they give you LLM, especially LLMs, and can give you an answer which may not be real. So how you avoid that nonsense answers to some important questions. So that's one of the challenge. And last but not least, security. I mean, energy industry is high fidelity, high risk environment. So how you make sure that you are not exposing your operational data directly to these LLMs. So those are some of the challenges, and I'm going to show in the next slide how we try to address that. So what our approach is like taking all that dispersed operational database, alarm data, network data, and build a LLM, a large graph model where each node is connected with each other based on the network connectivity. And then you are also representing each device which is connected to the nodes, like your relays, sensors, whatever it is, and all in a one graph model, single graph model, which can be easily queryable by LLM. So how we are doing it? So once you have this large graph data model built, then you can simply user can simply ask a question, and LLM will convert that question into a query, and that query will actually go and extract the information from the graph model, and then take it back to the user and output the results. So what we are doing here is, and when I was talking about the network security, so here we are not exposing the operational data to the LLM, but we are actually just training LLM on the queries. So queries are the one which LLM gets trained on. So like, for example, what are the active alarms? Are there chattering in the alarm? Those kind of user prompts are getting trained, and then queries getting generated. So we are not exposing the alarm data directly to the LLM. So that's one way we address. So, and from a security perspective, from hallucination perspective, if that query does not, or if that query does not exist and LLM is not trained on, it will just return that query is not recognized. So that way also we are trying to avoid any hallucination which LLM can do. So just give an example, the way like user can go in the Alarma tool and can simply enter, okay, what are the chattering alarms? Give me a summary of all the chattering alarms. So it will basically display all the alarms in a table where expert operator can just quickly see, but it will also give you explanation of all the chattering alarms for a new operator or somebody who's trying to from a learning perspective, they can quickly go and also see more detailed explanation. So there is a lot of explanation, gives us very powerful baseline tool to look at all the operational data sets together. And what one quick example is, if you have a storm happening in the system, you can just quickly look at those alarms and just say, okay, based on those alarms, these are the lines which are out, and just it will be able to quickly tell you. So that's basically what we're trying to do is here, making this alarm management much easier and accessible for an operator perspective, and also making sure that we are having more perspective of the alarm and the network together, so that operator can see what is going on in the system. So that's one area, and there are other AI applications we are working on, but this is one of the novel one which I wanted to present today. Another area we're working on is looking into oscillation detection and monitoring, and that's one of the main things which we have, in the Iberian blackout or other recent events we have seen. So we are looking at both from forced oscillation, natural oscillation, as well as subsynchronous SSO, high frequency oscillations as well. From a forced oscillation perspective, what NERC recommends is that you should be able to detect the oscillation, you should be able to characterize the oscillation, and then you should be able to identify the source of the oscillation and remove that energy from the system so that so that the issue is addressed. So for that, we have developed a tool called forced oscillation localization tool. It based on various methods and dissipating potential method. I know Slava is there. He's one of the main who has developed that method. But what the tool does is tool can help you basically just looking at the PMU data can help you. Okay, what is the source? And look source of the oscillation, what type of oscillation, whether it's originating from like an active power malfunctioning or reactive power not or controls not tuned properly. It can also tell you whether the oscillation is inside the territory or outside the territory. The main advantage of this tool is does not rely on the topology and does not need 100% or full observability of the system. Even with the partial PMU observability, you'll be able to detect the oscillation and the source and where is it. We've been testing and validating this tool with actual events, and just a quick example I'm going to show in the next slide is looking into different kind of events. So one event which is mainly originated from a data center, a reactive related to reactive power issue. So we validate that using so it was able to tell where the source is. Also, what is the damping ratio of it? What kind of oscillation is it? We also look into different oscillations, looking originating because of a hybrid plant. We also look into oscillation related to synchronous motors driving reciprocating compressors and all. So the tool, just making sure that it captures and able to detect all these oscillations or not. So that's one area definitely we're actively working on. Another thing I want to highlight from a natural oscillation is obviously that's a inherent characteristic of the system when you have different group of machines bouncing energy against each other and you start seeing these inter-area modes and oscillations. So how can you use different way, like very traditional way is to damp those oscillation is your power system stabilizer. But now since your generation mix is changing and you're retiring a lot of synchronous machines, that those stabilizers may or may not be online at that time. So how can you use other means of damp those kind of oscillations? So very interesting work we did with Italian utility Terna, where they actually now have it in field, where we are using the PMU data, which basically looking at the frequency measurements. Those frequency measurements goes back to the control center, and then control center, we have a wide area damping controller sitting there, and it basically sends a signal to actuator, and in this case is a synchronous condenser, which basically whenever it sees an oscillation, which was around like 0.3 hertz, and as soon as it sees that, it should be able to send a signal to actuator, and the synchronous condenser will be able to damp that oscillation. So that's one of the ways, looking into more other means of doing more autonomous wide area damping kind of control. If your traditional system like power system stabilizers and those are not available, or some of the machines which have retired where those power system stabilizers were installed. So that's one thing we are looking into. Also not relying on more centralized control, but also looking on more decentralized control. So centralized controls typically are much slower, and now we have seen that you have a lot of IBRs in the system. For example, you can use the power oscillation damping capability of these IBRs to suppress some of these oscillations locally. So looking into that also from a more decentralized kind of control, how can you use PMUs and other devices to damp those oscillations. One thing which I did not mention is some of the things like these high frequency oscillation or because of the subsynchronous oscillations, those PMU cannot capture. So there is a lot of research now in industry on how synchronized waveform measurements can be used to detect those kind of oscillations. So a lot of work going on in that area as well, which I don't think I have time today to present. But in general, just wanted to give you a flavor from starting from control center of the future vision. What do we need, what tools we need, and then going towards how we can leverage these new technologies, AI, how we can leverage sensors and other things to provide decisions or improve decision support from an operator perspective. So right on time. Yeah. Thank you.
Thanks. Okay, our last panelist is Jonathan from ISO New England, which is near and dear to my heart. Best ISO out there, all regards to ERCOT.
How do I don't know where the. One more time. There we go.
Victory.
All right, thank you. Thanks, John. So my name is John Gravelin. I'm the Senior Manager of Control Room Operations for ISO New England. And I kind of think I should have gone first because I'm about to tell you all the problems and the complexities that I see within our control room. And then they already solved all these problems for me. So it's the chicken or the egg right now. So I'm going the wrong way. So it's a little about me. The important part on there is I've been in the power industry for about 26 years. 21 of that have been in the ISO New England control room. So I've seen the power system progress from the way it used to be to where we are today and moving into the future. And I've gotten to see how complex it has become and how fast it has gotten there. So what we see today is a drastic increase in variables that are demanding our attention and impacting our operations. And along with those variables, we see the risk increasing and our resilience and our ability to adapt to these changes decreasing as we move forward. So in the old grid, we were positioned with large centralized generating stations that flowed pretty much in one direction from onto the transmission system to the sub-transmission to the distribution and then to feed the load. We also had to deal with changing weather, but as long as we knew what day of the week it was, whether it was a holiday or not, and what we could expect for temperature and the type of weather conditions, we could pretty much predict what we were about to see, and we could do that with pretty high accuracy. Now, as the grid is changing, we're rapidly progressing and developing new technologies, installing these new technologies, which are much smaller and widely dispersed. We have a lot of new players that are entering the markets and in the industry because they see a financial incentive to do so, and they're not all well in tune with how a power system is supposed to operate. And then we have additional engineering challenges. All these new technologies coming on the system, they're not necessarily designed exactly the same way. Their power controllers could be different depending on the installation. And where they connect into the distribution or the transmission system presents some new challenges to us. And then we're adding other variables for weather beyond what we already talked about. And John hit on some of these earlier. We need to deal with wind speed and direction and the variability of that. The probability of that. We go into a lot of discussions about probabilistic forecasting and things like that. And irradiance. It's difficult to forecast when a cloud is going to drift over one of your large solar fields and wreak havoc in that respect. So all of these new variables are coming into play, and we as system operators need to deal with that. So us as an operator or a system operations control room, we have to deal with zero tolerance for error. Nobody wants the power grid to go down. Nobody wants us to make mistakes that impact the reliability to the system. So now we're dealing with rapid change and highly stressful conditions, and the grid is kind of outpacing what we can handle as far as transmission and the tools that we had 5 years ago to deal with things. We need to adapt and overcome those challenges. So I was at a NERC conference last week, and this gentleman brought up this point, and it kind of resonated with me. It's kind of true, and it reflects on all the things that we do in the power system control room. Power system supply will always equal demand, even if that demand is zero. That is our objective, not the zero part, but to make sure we're balancing supply and demand every second, every minute of the day to ensure that we're operating the most reliable and dependable grid that we can. So that kind of hit me, and I'm like, I'm going to use that. I'm going to steal that. So what's driving this complexity? And I think the first thing we can attribute it to is the policy accelerator. So we have a lot of, within New England, we're made up of 6 states, and each one has their own green policies, and we deal with how they interact with each other and how they play into the market. But overall, these green mandates are a decisive force in why we're moving in this direction. These incentives encourage rapidly deployable, small, flexible resources to integrate into the system. And most of them are PV or wind or even BESS at this point. We're starting to see the batteries. We don't have anything near what ERCOT or California ISO have, but we're up around 500, I'd say at this point. I think we'll see 700 megawatts at the end of the year, but we're seeing larger and larger installations. So these are coming, and we're learning how to deal with them. And then, as I said earlier, it's forcing a shift from centralized power plants to these small distributed resources that now we have to deal with in a two-way flow onto the power system, rather than going from transmission to subtransmission to distribution. Now we're seeing the distribution actually generating energy, and we have to move that around the system, which is kind of a challenge for our modeling teams to deal with. And again, it's happening very rapidly. So what else is driving this complexity? It's the physics of the system. As we've seen with areas like Spain and the blackout that occurred there, we're losing inertia. We're losing rotating mass with the incorporation of these IBRs and small variable resources. And I understand the controllers can create virtual inertia, but I'm still not convinced it's exactly the same as having large generators out there spinning that can dampen out disturbances and oscillations. So these are complexities that we have to learn to deal with, and our engineering folks have to address, and we're moving forward into this kind of unknown region where we see small impacts based on this already, but it's going to be faster and more severe and more impactful as we move forward. And then we have the infrastructure bottleneck. In the past, we had a lot of onshore wind facilities that were interconnecting in very remote regions, such as northern Maine. They were interconnecting where the transmission system wasn't necessarily the strongest, but they fit at the time, and we ended up with a lot of congestion. And that happened all throughout New England, not just in Maine, but northern New Hampshire and Vermont as well. We end up with these interfaces with many resources buried behind them that we have to deal with the congestion that they cause, and we're curtailing all this clean energy that needs to get to market. In addition to that type of infrastructure, the transmission infrastructure, we have technical delays in EMS and software that's being challenged to deal with these large number of new variables being put onto the system, all this new generation that we have to build into that model and learn how to deal with in different ways than we dispatched generation in the past. So what is our crisis right now? And I think one of the main things that we deal with today is what we'll call information fog. We get a lot of information into a control center that's operated by 5 system operators. I'm going to use an example of June 24th. June 24th, we had an event in the control room that it wasn't a critical event, but it was very high profile. We dipped into our secondary source of reserves. So it's kind of the pinnacle of our operations over the summer. And on that day, in the 12-hour shift around when this period of time occurred, we received 470 calls into the control room. So I have 5 operators answering 470 phone calls. Those 470, 290 of them were directed at 2 desks. And those desks are responsible for real-time dispatch of the system on a 10-minute basis. And the other one is handling the interchange schedules with our neighboring control areas. They're very busy, just performing their normal tasks. And then their secondary tasks, being the point of contact to our generators, is overwhelming. And if I can pare that down a little bit more, in the 5 hours surrounding the event, I think that call volume was 350 calls. So you can see when those occur. They occur at the time you don't want the phone ringing, that you need to focus on other things. In addition to that, we had about 700 redeclarations in that time period, meaning generators are contacting us and we need to enter data into our software systems manually. And that happened about 700 times in that time period. So lots of things going on. Lots of things we could address with AI and with software automation that could make our operators' lives easier. And on top of the information overload, you have the human factors. You're wearing out your system operators. You're tiring them out and focusing them on areas that they probably don't need to be focused on. That there's more important things we could be looking at. And then we have cybersecurity, and we all have to be aware of that and how it impacts the data and the tools that we're receiving and the tools that we're using. Oh, I went the wrong way. Sorry. And this just goes again to show all these things that are feeding into the funnel of operational decisions and all meeting at that decision point. We talked a little bit about the risks that we have. I'd like to see a lot more automation of those phone calls and that data, but we also have to address the out of the loop syndrome. If all of these pieces of information are coming in through an automated means, what's making the operator aware when that critical piece of information gets passed on and we miss it? So that's where things like AI and software alarming could be enhanced to get us out of that out of the loop syndrome, take the burden off the operator, but still focus on the important things that need to be addressed. And in conclusion here on this slide, it says, we're managing low probability but high impact events with zero margin for error. That is our challenge. We can't make errors, but we don't experience these events frequently. So we need to be able to train on these tools and utilize these tools in simulations and scenarios, while also being able to depend on them in day-to-day operation. So what are our pillars for success? And I already touched on some of these. But the first line, first course of action is to implement things like AI, machine learning, and software automation. And I think it's funny, somebody was talking about hallucinations, and I was focused on how dependable is AI and how much would I trust it. So I told AI, I think it was Google or Copilot, I'm not sure which tool I was messing around with at that point. I said, give me a map of the New England states. Pretty easy, right? It probably hasn't changed in 250 years. It's the same 6 states, same map. And this is what it gave me. And if you look up here, I think AI feels that we should incorporate Texas, where Rhode Island is. Give me California off the western side of Connecticut. Throw a little Nevada in there. And then it wouldn't change it. I was telling AI it was wrong and to provide me something different, and it refused to change this map. And I said, I'm going to throw this in here just as an example of these hallucinations and these problems that AI still has. I understand it's still in its infancy, but it's a good example of why AI will never replace my system operators. It will always be there to make us better, to make us more efficient at what we do, or to take our focus away from things that aren't very necessary and allow us to focus on the things that are detrimental and we need to address. But you'll always need some type of human intervention to second check the AI, because Texas is nowhere near Massachusetts, although it feels it should be. And then how else can we improve this? And it goes a little bit beyond the control room, but it speaks to some of the points that all of these folks brought up today. the incorporation of grid enhancing technologies, batteries, flow control, dynamic line ratings, AARs, which we're all focused on today. But all of these things make us more resilient and adaptable. But again, we have to learn how to use them properly and effectively in our system operations. And then really the meat of this is who fixes it. So we talked about tools and I brought up the complexities we deal with, but we need the talent and the diversely skilled and educated personnel in order to operate all these things. Not just system operators, but we need IT staff to develop these tools for us and to maintain these tools and these new models. And that's important to us as ISO New England, but in the industry overall. If we don't have these people out there developing the tools that we can utilize, we are doomed to fail, and we will not have the tools we need to succeed in these highly variable situations. So outreach to universities and development of intern programs to engage these young people when they're young and they can realize that, hey, the power system is this really cool thing that I really want to be involved in. And I've seen it with my own eyes. Electrical engineer knows nothing about the power system, but ends up doing an internship for a small transmission company. And all of a sudden his eyes are open to this new world that he knew existed, but he wasn't really introduced to. And they go back to college and they're all power systems all the time, and that's their drive, and that's what they want. So that's important, that we need to develop that and foster those things in all levels of our industry. And then finally, policy. So policy was one of my main drivers when we got to this point. But I think it's a very important place or a pillar of this strategy for success. We have 6 states in New England, and all of them have 6 different rules to how they implement their green agenda. Aligning these states, and I'm not going to say just in New England, it's across the country and across the world, aligning these goals and these initiatives, although it's difficult to do, it would greatly help us in operating the power system and be more successful. So more outreach to our policymakers would be very helpful in this. And this just summarizes the goals, but again, it's better tools, more effective AI, but ultimately a more capable and empowered workforce that's educated and that we put time and effort into retaining and providing them opportunities. So all of those things are my concerns and my ideas for moving forward in this. So thank you.